Previously, we covered the core foundations. Now, in part 3, we tackle Moon, origin theories. Moon. Episode 3. Origin theories as time. We looked at the Moon's geology, its surface, its craters, and what lies beneath that ancient, battered crust. Today's question is simpler to ask than it is to answer. Where did the Moon come from? You'd think we'd have settled this by now. We've been studying the Moon for centuries, sent people there, brought back samples. And yet its origin remains one of the most actively debated problems in planetary science. The leading theory is compelling and well supported by evidence. But every time we think we've nailed it down, something new complicates the picture. That tension is exactly what this episode is about. This is Orbital Dispatch. Let's get into it. To understand why the Moon's origin is such a puzzle, you first need to appreciate how unusual the Moon actually is. Most moons in the solar system are relatively small compared to the planet they orbit. Ours isn't. It's about 2,159 miles across, roughly a quarter of Earth's diameter. That makes the Earth-Moon system closer to a double planet than a conventional planet and moon pairing. It's the fifth largest moon in the entire solar system, and it orbits a rocky terrestrial planet, which makes it particularly unusual. Its gravity is about a sixth of Earth's. Surface temperatures swing from around 260 degrees Fahrenheit in direct sunlight to negative 280 degrees in shadow. There's no significant atmosphere, just a thin exosphere made of atoms kicked off the surface by solar wind and micrometeorite impacts containing traces of sodium, potassium, helium, and hydrogen. Nothing you could breathe, nothing that would protect you. Its average distance from Earth is around 238,900 miles. One orbit takes about 27.3 days. And because of a process called tidal locking, that orbital period matches the Moon's rotation rate almost exactly, which is why we always see the same face. All of that is well established. But it raises a question that took scientists a very long time to even approach properly. How did an object this large end up in orbit around Earth in the first place? Several answers have been proposed over the years. Before we get to the one that currently holds the most weight, it's worth understanding why the earlier ideas failed, because their failure is actually what makes the leading theory so interesting. The first serious hypothesis was co-formation, sometimes called the binary accretion model. The Earth and Moon formed together from the same cloud of gas and dust at roughly the same time, in the same region of the early solar system, the way some binary star systems form. Two separate bodies that simply grew up next to each other. Tidy idea. The chemistry doesn't quite work, though. If both bodies formed from the same material in the same region, you'd expect similar compositions, and in some ways they do match. But the Moon has a much smaller iron core relative to its size. Earth's core accounts for roughly 30% of its mass. The Moon's is only about 1 to 3%. Co-formation doesn't explain that gap. The second hypothesis was capture. The Moon formed somewhere else in the solar system, drifted close to Earth, and was pulled into orbit by Earth's gravity. Plausible on the surface, and it would account for some compositional differences. The problem is that gravitationally capturing an object this size requires some mechanism to slow it down at just the right moment. The physics can be made to work in theory, but the probability is so low that most researchers were never particularly satisfied with it. The third hypothesis is the strangest of the three, though it was taken seriously for a time. It's called fission. Originally proposed in the late 19th century by George Darwin, son of Charles Darwin, the idea was that early Earth was spinning so fast that a chunk of material broke off and flung outward, eventually settling into orbit. The Pacific Ocean basin was even suggested, at one point, as the scar left behind. Dramatic, also wrong. The angular momentum required for Earth to spin fast enough simply doesn't match what we observe in the Earth-Moon system today, and the Pacific formed through entirely different geological processes. So by the 19th, planetary scientists had 3 hypotheses and serious problems with all of them. Then came the Apollo missions. Between July 1969 and December 1972, 6 Apollo missions landed on the Moon and returned approximately 842 pounds of lunar rock and soil. For the first time, geochemists could actually analyze what the Moon was made of in proper detail. What they found was striking, and in some ways puzzling. The lunar samples showed that the Moon and Earth share nearly identical oxygen isotope ratios. Isotopes are different versions of the same element. Same number of protons, different number of neutrons. The ratio of oxygen isotopes acts almost like a fingerprint for where in the solar system material formed. Objects from different regions tend to have different ratios. Earth and Moon have ratios that are almost indistinguishable. That ruled out capture fairly decisively. A body from a different part of the solar system should have a different isotopic fingerprint. But the samples also confirmed the Moon's iron depletion and revealed something else that needed explaining. The Moon is depleted in volatile elements, things like water, sodium, and potassium, that evaporate at relatively low temperatures. Whatever formed it involved very high temperatures. That combination, similar isotopic composition to Earth, iron depletion, volatile depletion, and sheer size, pointed researchers toward a new idea formally proposed at a conference in 1984. It became known as the giant impact hypothesis, and it went something like this. Around 4.5 billion years ago, the early solar system was chaotic. The inner solar system was crowded with planetary embryos, bodies that had grown to roughly the size of Mars or larger, gradually sweeping up material from their orbits. Earth was one of them, but it wasn't alone in its orbital neighborhood. There was another planetary embryo, referred to by convention as Theia, probably similar in size to Mars, roughly half Earth's diameter. At some point, Theia's orbit became unstable, and it collided with the proto-Earth. This was not a gentle collision. High energy, involving 2 substantial planetary bodies, more of a glancing blow than a head-on impact, according to the models. The iron cores of both bodies merged, which is why the Moon ended up iron poor. Most of the metal sank into what became the new, larger Earth. The outer, silicate-rich material from both bodies was blasted outward in a vast disk of vapor and debris. Within a geologically short time, estimates vary from a few thousand years to tens of millions, that disk coalesced under its own gravity to form the Moon. The heat involved would explain the volatile depletion. Temperatures in the impact debris would have been extreme, driving off easily evaporated elements. The isotopic similarity to Earth would make sense because much of the material came from Earth's own outer layers. It fitted the evidence better than anything before it, and by the early 1990s, it had become the dominant hypothesis. Here's where it gets complicated. The giant impact hypothesis has been refined many times since 1984, and each refinement has come because the data keeps throwing up new problems. One significant issue: if Theia formed in a different part of the solar system from Earth, it should have had a different oxygen isotope ratio. The Moon's, however, matches Earth's almost perfectly. You'd expect at least some contamination from Theia's material, a detectable difference. In most simulations, it doesn't come out that way. Various solutions have been proposed. Some researchers suggest the impact was so energetic that the debris was thoroughly mixed, homogenizing the isotopic composition. Others propose that Theia formed close enough to Earth to have a similar fingerprint to begin with. Some newer models invoke a much more energetic impact, a larger impactor, a more violent collision, a more thoroughly mixed debris cloud. There are also models that flip the geometry entirely. Some researchers have proposed that the impactor and Earth were closer in size than originally thought. almost equal partners in the collision, producing a rapidly rotating proto-Earth and Moon system that later slowed down through gravitational interactions with the Sun. None of these variants has fully resolved every tension in the data. Reanalysis of Apollo samples with modern equipment and results from more recent missions have continued to add detail and occasional new complications. There's ongoing debate about how much water was actually lost during the impact, because some measurements suggest the Moon may have retained more than the simplest models predict, particularly in permanently shadowed craters near the poles. What all of this tells us is that the giant impact hypothesis is not a finished answer. It's the best available framework. The broad strokes are well supported. A large impact, merger of iron cores, ejection of a debris disk, formation of the Moon from that disk. The finer details, the exact size of Theia, the geometry of the collision, the degree of mixing, are still being worked out. That's normal science. It's not a reason to doubt the basic model. One more thing worth noting, and it's easy to overlook. The Moon's formation wasn't just consequential for the Moon, it was consequential for Earth. The impact almost certainly reshaped Earth's interior. Theia's iron core merging with Earth's contributed to the size and character of our own core, which drives the geodynamo that produces Earth's magnetic field. That field is part of what shields our atmosphere from being stripped away by solar wind. Without it, Earth's surface environment would look dramatically different. The Moon also stabilizes Earth's axial tilt. We're currently tilted at about 23.5 degrees relative to our orbit, and that tilt is what gives us seasons. Without the Moon's gravitational influence, models suggest Earth's axial tilt could vary much more dramatically over long timescales, potentially destabilizing climate in ways that might have affected the conditions for complex life to develop. This isn't a certainty, and it's an area of ongoing research, but it's a genuine consideration in how we think about planetary habitability. The Moon isn't just an interesting geological object. In a real sense, it's part of why Earth is the kind of planet it is. The question of where it came from still has edges that science hasn't fully mapped. But the picture that's emerged, a young, violent solar system, a catastrophic collision, a disk of debris slowly pulling itself together under gravity, is one of the most dramatic origin stories in planetary science, supported by real evidence, real samples, and decades of rigorous modeling. Next time, we turn from how the Moon formed to how we've explored it, from the first robotic probes to the Apollo landings, and to the missions currently planned for the years ahead. If you want to follow the full series from the beginning, the playlist is linked in the description. Each episode builds on the last. If you find this kind of science worth following, subscribing is the simplest way to make sure you don't miss the next one. This is Orbital Dispatch. That is part 3 of Moon. In part 4, we explore the next key question. Subscribe so you do not miss it.